Hello friends, in previous video we had discussed about the logarithm of complex number. So today in this video we will be discussing about the different types of sum of this chapter, and this video will be the last video of this chapter. From the next video we will be starting the new chapter. Okay, so the first numerical is prove that sine z is analytic everywhere. So the solution, sine z equals to f of z. Okay, so let f of z is equals to sine z. Now we know that we can write u plus iv in the place of f of z, and in the place of z we can write x plus iy. Okay, now according to the formula of sine of a plus b, we can expand this sine a into cos b plus cos a into sine b. So according to this formula we will expand this term. So this is u plus iv, which is equals to sine x into cos of I into y, because here x is a and b is iy, plus what is cos a? So it is a is x, so cos x into sine b, b is I into y, so it is I into y. Okay, so this is u plus iv, which is equals to sine x. Now in previous video I had given some important results which are here. Okay, so according to this result, this cos of iy can be written as cos hyperbolic y, and sine of iy can be written as I sine of hyperbolic y. So cos of iy will be cos hyperbolic y plus cos x. And what is sine of iy? It will be I into sine hyperbolic y. Okay, so now we will separate the real part and the imaginary part. So now u equals to sine x into cos hyperbolic y. So this is the real part, and v is the imaginary part. So it is sine hyperbolic y, this term, because these have I. So it is sine hyperbolic y into cos x. Okay, so this is the real part and the imaginary part. That is u equals to sine x into cos hyperbolic y, and v is equals to sine hyperbolic y into cos x. So now to prove analytic, we want the CR equation to be satisfied. That means ux is the partial differentiation of this u with respect to x. So now what is ux? So this differentiation of sine x with respect to x will be cos x, and this as it is cos of hyperbolic y. And what is ui? Ui is the partial derivative of u with respect to y. So it will be sine x as it is, and cos of hyperbolic y. This is not the normal function as cos theta. It is the cos of hyperbolic, means hyperbolic of cos function. So the derivative of this cos hyperbolic y will be sine hyperbolic y. If it was cos x, then the derivative of cos x will be minus sine x, but here the function is hyperbolic, so cos hyperbolic y will derivative of cos hyperbolic y will be sine hyperbolic y. Okay, and here vx, so sine hyperbolic y as it is, and here cos, so it will be minus sine x. Okay, and vy will be derivative of v with respect to y. So here it is sine hyperbolic y, so it will be cos hyperbolic y. Derivative of sine hyperbolic y will be cos hyperbolic y, and cos x as it is. Okay, now what is CR equation? That is ux should be equals to vy, and uy should be equals to minus of vx. Let's see these equations are satisfied or not. So now ux is this is cos x, and vy, this vy. So we have cos x, and also cos hyperbolic y, and also cos hyperbolic y. So this equation is satisfied. Okay, so now we will see uy equals to minus of vx. So uy have sin x, and vx also have sin x, and uy have sin hyperbolic y, and vx also have the sin hyperbolic y with negative sign. So this is the equation which is satisfied. Okay, so this equation is also satisfied. So we can say that CR equation is satisfied everywhere. Okay, now as in the denominator of ux, ui, vx and vy there is only a constant term 1. We don't have any variable in the denominator, so we can say that ux, ui, Vx and Vy are continuous everywhere. Continuous everywhere. Okay. So now as CR equation is satisfied everywhere and these functions are continuous everywhere, so we can write that the given function f of z is equals to sine z is analytic everywhere. Analytic everywhere. Now as the function is analytic everywhere, the function is entire, therefore sine z is entire. Okay, this is the extra part. This is our question, that we have to prove that sine z is analytic everywhere. So we had proved our question, and the extra part is the, as the function is analytic everywhere, the sine z is entire. Okay. So now the next numerical is find the analytic function f of z if u minus v equals to e raised to x into cos y minus sin y. So this numerical is very important. So observe this numerical very clearly. Okay. So now first we know that function f of z can be written as u plus iv. Okay. Function f of z can be written as u plus iv. Now here we have u minus v. So observing this term, we get an idea that we have to multiply this equation with 1 plus I on the both the side. So multiplying with 1 plus I on the both the side of the equation, we get 1 plus I into u plus iv. So now let this whole term is written as capital F of z. Okay, this is only the notation. This whole term is written as capital F of z. Now open this bracket, that is u 1 into u 1 into iv. So it is 1 u plus iv plus this I into u plus I into iv, that is plus I square into v, plus I square into v. So this capital F of z is equals to u plus iv plus I into u minus v. Why minus? Because I square is minus 1. Okay. So here we get u minus v plus I into bracket u plus v. So this is capital F of z. So we got the u minus v. Okay. So now let this f of z, let this we write as capital U plus I into the whole term as capital V. Okay. This is just a notation. So this equation we had derived. Now in our question we have u minus v. So what is u minus v? It is capital U. So capital U, which is equals to u minus v, which is equals to e raised to x into cos y minus sin y. Okay. This led equation 1. Now this capital U is equals to e raised to x into cos y minus sin y. So now we have to find the analytic function f of z. So according to the Milne-Thomson method, here u is given. So we will write the formula of analytic function according to Milne-Thomson method. So now according to the Milne-Thomson method, as u is only given, so we can write the analytic function capital F of z is equals to ux integration of ux at z0 dz minus I into integration of uy at z0 dz. We had write here capital F of z because we had derived an equation which relates the u minus v with the capital U. So we have to write the capital F of z. In the question it is given that we have to find the small f of z. Okay, so we will find small f of z, don't worry. So here capital F of z is equals to integration of ux at z0 dz minus I into integration of uy at z0 dz. That means we have to find the capital U of x. Now what will be u of x? Here capital U is given, that is e raised to x into cos y minus I into sin y. So u of x will be e raised to x into cos y minus sin y. Okay. And u of y, here it will be e raised to x into this cos y will be minus sin y minus cos y. That means it will be minus of e raised to x into sin y plus cos y. Okay, so this is u of y. Now we have to find u of x at z0. So u of x at z0 means we have to put z in the place of x and 0 in the place of y. So we will put, so it will be e raised to z into cos 0 minus sin 0. So what is cos 0? It will be 1 and sine 0 it is 0. So it is e raised to z. Okay. So now we have to find u of y at z comma 0. That means we have to put z in the place of x and 0 in the place of y. So we will write here that is minus e raised to z. Now what is sine 0? It is 0, and what is cos 0? It is 1. So it is minus of e raised to z. Okay, so now we will put the value of u of x at z0 and u of y at z0. Okay, so this capital F of z is equals to integration of e raised to z dz minus I into integration of minus of e raised to z into dz. So this minus and this minus gets addition, so it will be e raised to z into dz plus I into integration of e raised to z into dz. So this is e raised to z plus I into e raised to z plus c. This is capital F of z. Okay. So f of z equals to e raised to z as common, we get 1 plus I plus c. So now we know capital F of z is what? Capital F of z is 1 plus I into small f of z. We have to find small f of z. Okay, so capital F of z is 1 plus I into small f of z, which is equals to e raised to z into 1 plus I plus c. Now we will divide this 1 plus iv on both the sides. So we get f of z, which is equals to e raised to z plus c upon 1 plus I. So this is the final answer. This is the analytic function f of z is equals to e raised to z plus c into 1 plus I. Okay. So now the next numerical is prove that f of z is equals to under root of mod xy when z is not equals to 0 and it is equals to 0 when z is equals to 0. Is not differentiable at z is equals to 0 even though CR equation satisfied at z is equals to 0. Okay. So this is another important question. So observe it properly. So now the solution is here function f of z is equals to under root of mod of x into y. Okay. So we know that function f of z can be written as u plus iv, which is equals to under root of mod of x into y. So now separating real and imaginary part, we get u equals to under root of mod of x into y and v is equals to 0. Why v is 0? Because we don't have any imaginary part. So it is I plus I into 0. Okay. So v equals to 0. So now in the question it is written that CR equation is satisfied. So first we will check this, that CR equation is satisfied or not. So here ux can be written as del u by del x. Okay. Now this del u by del x according to the definition can be written as limit h tends to 0 u of, here we are differentiating with respect to x. So u of x0 plus h comma y0 minus u of x0 y0 upon h. This is true when we have to differentiate it at point x0 y0. Okay. So this formula is important for this sum. So observe this formula perfectly, that is u of x can be written as del u by del x and it is differentiating at x0 y0. So we can write according to the definition limit h tends to 0 u of x0 plus h comma y0 minus u of x0 comma y0 divided by h. Okay. So here in the question we had given that at point z is equals to 0. Now z is equals to 0 means z is what? Z is equals to x plus iy. So when z is 0, that means x is also 0 and y is also 0. Okay. So in the question we had given that z is equals to 0. That means we have x0 and y0 as 0 comma 0. Okay. So del u by del x at 0 comma 0 is equals to limit h tends to 0 into u of, what is x0? It is 0 plus h comma 0 minus u of 0 comma 0 upon h. So now what is limit h tends to 0? What is u of h comma 0 minus u of 0 comma 0 upon h? Now what is u of h comma 0? So first we will see what is u. So here we have u is equals to under root of mod xy. So we have to put h in the place of x and 0 in the place of y. So if we put h in the place of x and 0 in the place of y, we get u equals to 0. So here limit h tends to 0, it is 0 minus u of 0 0 will be 0 only divided by h, so it is equals to 0. So we had obtained our first relation, that is ux equals to 0. Okay, so now we will find uy. So uy equals to del u by del y at point x0 y0, which is equals to limit h tends to 0 into u of x0 comma y0 plus h. Why y0 plus h? Because we are differentiating u with respect to y, so it will be y0 plus h minus u of x0 comma y0 divided by h. Okay, so it is del u by del y at x0 y0, which is equals to limit h tends to 0 u of x0 comma y0 plus h minus u of x0 comma y0 upon h. So we will write del u by del y at 0 comma 0, because we have x0 y0 as 0 0. So it is equals to limit h tends to 0 u of, what is x0? It is 0. What is y0? It is 0. So u of 0 comma h minus u of 0 comma 0 upon h. So we will write limit h tends to 0. What is u of 0 comma h? It is also 0, because we have to write 0 in the place of x and h in the place of y. So we get 0. We get 0. U equals to 0. And u of 0 0 is also 0 divided by h. So we get 0. Okay. That means u of y is also 0. Now as the imaginary part is 0, as v is 0, so vx is also 0 and vy is also 0. Okay, that means here we have ux equals to vy and uy equals to minus of vx. So we know that CR equation is satisfied. It satisfied at z is equals to 0. Okay, we have to prove that the function given is not differentiable even though the CR equation is satisfied at z is equals to 0. So now we know what we know, that according to the definition of differentiation, that f dash z equals to limit delta z tends to 0 into f of z plus delta z minus f of z upon delta z. This equation is true when we don't have the point at which we have to differentiate the function, but here we have the point, so we will use this for this equation, that is f dash of z0, which is equals to limit z tends to z0 into f of z minus f of z0 upon z minus z0. Okay, this formula we will use here because we have the point of differentiation. So here z0 is 0, z0 is 0, so we will write f dash of 0 is equals to limit z tends to 0 into f of z minus f of 0 divided by z minus 0. So f dash of 0 is equals to limit z tends to 0. What is f of z? Here in the question we had f of z, that is f of z is equals to under root of mod xy. Okay, so under root of mod of x into y minus f of 0 will be 0, because in the question it is mentioned that when z is equals to 0, f of 0 is f of z is 0. Okay, divided by z. So here we have x and y, so we have to convert this whole equation in terms of x and y only. Okay, so this f dash 0 is equals to limit. Now when z tends to 0, that means z is equals to x plus iy, so x also tends to 0 and y also tends to 0. So here we will write, that is when z tends to 0, x also tends to 0 and y also tends to 0. So this is under root of xy minus 0 divided by x plus iy. Okay, so now we will use the path method. According to path method, first we will check along the x-axis, along x-axis. Now along x-axis y is 0. Okay, now as y is 0, we can write limit x tends to 0 into Now as y is 0, so if we put here y equals to 0, then we get 0 minus 0 upon, if we put here y equals to 0, that means we will get x only. So we will write x. Okay. So it will be equals to 0. So this is our equation number 1. Now we will see along y-axis. Along y-axis x is 0. Okay. So we will write f dash of 0 is equals to limit y tends to 0. Now when x is 0, then if we write here 0, we will get 0 minus 0. So 0 minus 0 divide by, here we have to write x is equals to 0. So 0 plus I into y. 0 plus I into y. So it is again 0. Okay. So now as these two equations is same, so we have to check the third. That put y is equals to mx. That means f dash 0 is equals to limit x tends to 0. We have to put y is equals to mx in the equation here. We have to put y is equals to mx. So it is limit x tends to 0 under root of x into m into x minus 0 upon x plus I into m into x. Okay. So limit x tends to 0 here under root of mod of m into x square upon x into I plus 1 plus x into 1 plus I into m. We had taken the x common from the denominator. So we get x into 1 plus I into m. So it is equals to limit x tends to 0. Here x square can be taken as out. So when x square comes out of the square root, we get x. So it is under root of mod m upon x into 1 plus I into m. So this x and this x gets cancelled. So here limit x tends to 0. But here in the term we don't have any x. Here the term is constant. So the limit of constant is constant. So we will write under the square root mod m upon 1 plus I into m. Okay. That means for different value of m, we get different answers. Okay. That means equation 1, 2 and 3 are not same. Equations 1, 2 and 3 are not equal. That means the limit of function f of z at z is equals to 0 does not exist. Okay. Now as limit does not exist, the function f of z is not differentiable at z is equals to 0. Okay. So that's all. These are the different types of sums which you will encounter in this chapter. So if you had any doubts, please ask me in the comment section. Please subscribe my channel for more educational videos, like and share. Thank you.